Hey there, guys. This is Mr. Herbst here, and I wanted to walk you through the stations, the review stations, that we did in class today. So I'm going to start here with Station 8, and I don't want to give away like all the information, so I really don't kind of want to like do everything for you guys because I want you to I want you guys to study, and so I want you guys to kind of like realize and go back and look things up and do stuff that you are supposed to be able to do for your test coming up soon. But anyway, this station here, Station 8, said, describe the energy transformations that are in the following picture. Well, here, the sun is nuclear energy. Nuclear. The sun relies on its energy source coming from the fusion between hydrogen power and it fuses hydrogen into helium. Okay, so in that process of the fusion of hydrogen into helium, some light and some heat is given off. So here we go, radiant heat comes down, it strikes a plant. So for example, it could strike corn, and that's chemical energy. So we go from nuclear energy to radiant to chemical energy, which is stored in the corn. And that chemical energy can go off and be processed in a little facility and be converted into ethanol. Ethanol is a type of fuel. It's kind of like gasoline, but it's actually a type of alcohol. And all of that, again, is chemical energy. And that chemical energy can be burned in a car. And that car is going to give off mechanical energy because it's a machine, it's moving, but a car also gives off a lot of heat as waste. All right, so the energy flow here is from nuclear in the sun to radiant of light coming off of the sun to chemical in the corn to chemical in the processing facility to mechanical and thermal in the car. So for this one here, I'm asking you guys to describe the relationship in the following equations. So if power increases and time stays the same, what happens to work? Well, you guys got to remember our equation is power equals work over time. Okay, so time needs to stay the same. So that number's not ever going to change. Power is going to go up. Okay, so the only way you guys got to think about it like this: what has to happen to W if T is going to stay the same? Well, T is going to also have to, or W is going to have to go up as well. So as power increases, work increases, assuming the time stays the same. Now the next one, if velocity is tripled, what happens to EK if mass stays the same? And I told you guys to assume that mass is 2 kilograms. So mass of 2 kilograms, so that's M. Velocity is going to triple. Well, here's the thing. So we do 1/2 times 2, which is 1, okay? And then v squared, so v is 3, so 3 squared is 9. So if you triple velocity, EK becomes 9 times bigger. And then for this one here, Station 6, what happens? What are the 7 types of energy we learned in class? And provide an example of each one. Well, there were 7 kinds of energy we learned in class. There's nuclear, there's radiant, which is light, there is thermal, which is heat, there's sound energy, there's mechanical energy, which is potential plus kinetic, there's chemical energy, and also there is electrical energy. So I'd like you guys to think about an example of each one, okay? I think I made a mistake on the slides there. Alright, here we go. Station number 5. Describe the difference between the law of conservation of energy and the law of conservation of mechanical energy. Well, the law of conservation of energy applies to the universe. It says that the law of conservation of energy says that the amount of energy in the universe stays the same. So E in the universe stays the same all of the time. It can go from form to form. It's going to change from all those different 7 types that I talked about in this last slide. It can change, but in the universe it all stays the same. But you know, whatever. Like human beings, you don't really care that the fact that the amount of energy stays the same. I mean, that's like just like kind of minutia, trivial facts to us. What we care about is how energy kind of behaves in machines that we use. So we care more about the law of conservation of mechanical energy, which concentrates more about how energy behaves in machines. And, you know, all machines have working parts, and all those working parts create friction. So, you know, friction creates heat, and heat is basically like waste. Like it's waste energy to us. So we don't really care too much about the heat that's given off by machines. It's like waste. So here's the bottom line. The energy that goes into a machine is never the same amount of useful energy that comes out of a machine. That's why I draw these arrows here, different sizes. Into a machine, you could have lots of energy, but coming out of a machine, there's definitely a lot less useful energy, because in machines, energy is lost as waste energy. Here we go, station number 4. It says complete the following diagram by filling in these bars. Alright, so this guy here, you know, this little guy here, stick figure, he's throwing a ball straight up in the air, and all of the energy is in the form of kinetic energy. As it goes up, it's losing kinetic energy. So we got to show here that the bar of kinetic energy is going to be smaller than it was when it started, but whoops, let me go ahead and erase these weird lines here. I need to zoom in here, guys. And you know, I'm kind of still getting used to how to use this explain everything. Alright, so when the ball is going up, it's losing kinetic energy, so that bar is going to go down. It's not going to be as high as it was before, and it's gaining potential energy, because, you know, it's going up in the air, so its height is increasing, so potential energy is increasing. When it's at its maximum height, like here in point C, it has it's going to have all potential energy and no kinetic, because it's not moving. And then when it goes back down again, it's going to be losing some potential energy, and then, you know, gaining some kinetic energy. And then when it's here, at point E, it hasn't gotten all the way down yet, so it still has some potential, but you know, it's going to have still you know, a somewhat filled bar of kinetic. Here we go, station number 3. What has more kinetic energy? Well, I'm going to leave you guys the opportunity here to figure this one out. Hopefully you did in class. The equation for kinetic energy is EK, so kinetic energy equals 1/2 mv squared. Alright, so you got to make yourself a list. We got mass is 3,000 kilograms, and we got velocity is 2 meters per second. So the first thing that you should do when you do your work is square this, 2 meters per second, multiply it by your mass, and then multiply it by half. So same thing for this bottom one here. A human moving with 60 kilograms, moving at 450 meters per second. You got to take this here, you got to square it, you got to multiply it by the mass, and then multiply by half. Alright, so I'm going to leave you guys up for that opportunity to get this one and figure out which one has more kinetic energy. Station number 2 here. How much horsepower does a 47 watt light bulb produce? And I gave you the conversion factor. This here is one of those factor label method problems. If you haven't figured out how to use the factor label method, well, you know, like I say in class, the knowledge for learning the factor label method isn't just going to hit you one day. You got to be able to do it. So, you know, maybe go to YouTube, you know, and type in the factor label method and figure out how to use it. The first hit there is a pretty good video. If you type in the factor label method on YouTube, the first one's a pretty good one. Alright, lastly here, the regular stations that you guys did today, we're figuring out in station 1 what car is more efficient, show all equations. Alright, so both of these here are asking you to find efficiency. Efficiency uses the equation percent efficiency is equal to energy out over energy in times 100. Okay, so in problem number 1, for example, I say a car takes in 45,600 joules of energy, but only puts out 12,000 joules. So this here, 45,600 is your energy in, and 12,000 is your energy out. Multiply by 100, slap a percentage sign on there, and you'll figure out what the percent efficiency of that truck is. Do the same thing for the second one and figure out which one is more efficient, the truck or the Prius. And lastly here, guys, this is station number 9. This one's kind of tough. I was asking you to fill in all the parts of the table. Now here's the thing. In this problem, I give you the height of the roller coaster in A, B, C, and D. I tell you the height. Okay, given the height of all of those, and given the mass, okay, you know the mass is 1,200 kilograms, because mass is never going to stay the same no matter where the car is, unless, you know, the car is you know, maybe like radioactive and just spewing out matter all over the place. But it's not, okay? It's a roller coaster. It's a regular old car. The mass stays the same. Right, so mass stays the same. So mass times gravity times height will give you potential energy. All right, so you'll be able to figure out this column, this column, this column, given the heights. All right. Then the other thing is you'll also know the total energy, because total energy is just potential energy plus kinetic energy. So you add those two together, you'll get total energy. So total energy stays the same the whole time because we're going to assume energy is conserved. All right, so all of those columns are the same. So after you figure out how much potential energy is there, you could easily figure out how much kinetic energy is there by taking the total energy minus the potential energy to get kinetic energy for all of these columns. All right, so I realize I went that pretty fast there. If you need to rewind, please do, and listen to it again, and try to see if you can get what you got out of it. After you get kinetic energy, though, you can use your equation for kinetic energy, 1/2 mv squared, to understand all of these velocity boxes. All right, so anyway, guys, that's the walkthrough here of the review session we did here in class today. And let me know if you guys have any questions. All right, I'm signing off. Have a good day.